Today's integral looks absolutely amazing. I mean, look at it. It's exotic, it's extravagant, it's just beautiful. And we're going to evaluate it using complex analysis, meaning that I'm going to invoke the residue theorem, which states that the integral over some closed contour C of a complex valued function f of z with respect to z equals 2 pi I times the sum of the residues of f of z enclosed by that closed contour. So for reference purposes, we're going to call our integral I, and we're going to introduce a complex valued function f of z being equal to e to the iz times log z divided by z squared plus 4. And this structure for our corresponding function in the complex realm may seem strange at first, but it's actually motivated by two things. Number one, this complex logarithm, and number two, the choice of contour. We're going to use the classic semicircular contour to evaluate this integral. So here I'm going to draw the complex plane where the x-axis represents the real part of the complex number z and the y-axis represents the imaginary part, and we're going to use a semicircular contour of radius r. That's a pretty bad drawing, so okay, better. So the semicircular contour of radius r, and because of this log z term up in the numerator, we need to avoid the singularity at z equal to 0. So we're going to circumvent that by using another semicircle, a smaller one of radius, let's say epsilon. Okay, cool. And as I said before, this choice of the function f of z is motivated by the complex logarithm as well as the choice of contour. And how do those two things actually add up to justify our structure here? Well, the reason is that part of your contour is on the negative half of the real line. And the coolest thing, in my opinion, the coolest thing about the complex logarithm is that it allows you to take the logarithm of negative numbers, like this number minus alpha, let's say. Log of negative alpha can be written as log negative 1 times alpha. So using the properties of the logarithm, we can write this as log negative 1 plus log alpha. And we know from Euler's wonderful formula that e to the I pi equals negative 1. So if we replace negative 1 by e to the I pi, then the logarithm and the exponential cancel out because they're inverse functions, correct? So you're left with I times pi plus the log of alpha. And if you look at the structure of our target integral, we need pi times sine of x and log x times the cosine of x. So because you're multiplying the complex logarithm by the complex exponential function, which is related to the circular trig functions, on multiplication you can recover these terms, and you'll see later in the video how this choice of function evaluated on this contour leads exactly to our target integral. Now, there is one thing I'd like to mention for those not familiar with complex analysis, not that familiar with complex analysis or contour integration, that is. This log that I'm writing, this log log, is not the base 10 log from early years. It's log with base e. It's the classic base e logarithm that we know as the natural logarithm. And many of you would think that shouldn't this be ln? Well, it's quite common practice to write log base e as the default log, as in if you write log, if you just write log, it's by default log with base e. It's not the base 10 log, it's the base e logarithm. It's also sort of a matter of preference as well. I mean, Flammy, in his videos on complex analysis and contour integration, he used ln. In my earlier videos, I used ln as well, and QNCube 3, he uses the log. So yeah, it's more like preference and practice, but there shouldn't be any confusion as to the meaning attached to this logarithm. With that out of the way, returning to what I said earlier, that these two integrals over the real line, they will recover our target integral. Well, let's see if this is the case. And remember, we're interested in the limiting cases of r going to infinity and epsilon going to 0. So the integral from epsilon to r approaches the integral from 0 to infinity of e to the I x. You can replace all the z's by x's now because we're on the real line. E to the I x times log x divided by x squared plus 4 dx. And what about the other integral, the integral from negative r to negative epsilon? Well, that approaches the integral from negative infinity to 0 of e to the I x times log x divided by x squared plus 4 dx. And if we perform a transformation here going from the x realm to the negative x realm, that'll take us to e to the negative ix times log negative x times, and the differential element here transforms into a negative dx term. And you can get rid of this pesky negative sign by just switching up the order of the limits of integration. So yeah, it doesn't look that weird anymore. So we have the integral from from 0 to infinity of e to the negative ix times log negative x divided by x squared plus 1. And again, this is where that awesome property of the complex logarithm comes in handy. Log negative x here equals log x plus I times pi. So that means this equals the integral from 0 to infinity of e to the negative ix times log x plus I times pi, and just multiplying out gives me e to the ix times log x plus I times pi times e to the negative ix divided by x squared plus 4 integration with respect to x. Okay, now let's go ahead and add these two integrals. Let's call this one I sub 1 and let's call this one I sub 2. So I sub 1 plus I sub 2 in these limits approaches the integral from 0 to infinity of e to the ix. If we factor out these log x terms, then we get e to the ix plus e to the negative ix times log x plus I times pi times e to the negative ix, all divided by x squared plus 4 and integrated with respect to x. And here, the sum of these two complex exponentials fits in quite nicely with the definition of the cosine function in complex analysis. So the cosine of x equals e to the ix plus e to the negative ix divided by 2. That means the sum of these two complex exponentials equals twice the cosine function. So yeah, this is awesome. We already have one of the terms we needed. We needed the cosine of x, twice the cosine of x times log x. And what about this term here? Well, we have e to the negative ix times I times pi, and once again, using Euler's wonderful formula, we know that e to the negative ix equals the cosine of negative x, which is of course equal to the cosine of x because it's an even function, plus I times the sine of negative x, and sine is an odd function, so we have cosine x minus I times sine x. And if you multiply by I times pi, we get I times pi times cosine x minus I squared times pi, and I squared is negative 1, so the two negatives cancel out. We have pi times the sine of x, and this equals the other term up here. Okay, cool. That means I sub 1 plus I sub 2 approaches the integral from 0 to infinity of twice the cosine of x times log x plus all of this junk here. That's pi times sine x divided by x squared plus 4 dx. And I'm going to separate this imaginary part here. We have I times pi times the integral from 0 to infinity of the cosine of x divided by x squared plus 4 dx. That was extremely cool. So we can replace the sum of these two integrals by our target integral I. And what about the integral over the closed contour? Well, the integral over c equals 2 pi I times the sum of the residues of f of z enclosed by our contour. So let's just refer back to our contour, and I'm just gonna copy and paste all of this stuff down. Okay, much better. So our function f of z was defined as e to the I z times log z divided by z squared plus 4. So the poles of the function are where z squared plus 4 equals 0, which implies that z equals plus or minus 2i. And our semicircular contour is in the upper half of the complex plane, so it only encloses one of these two poles. And it's a simple pole over here at 2 on the imaginary axis. Okay, cool. So the residues here are pretty easy to calculate. This implies that the integral over c equals 2 pi I times, now for the residues, we need the limit as z approaches 2i of z minus 2i times our function e to the iz times log z divided by, you can factorize the denominator in the complex realm as z minus 2i divided by z plus 2i. So you have some nice cancellation going on here, and you're left with 2 pi I times e to the 2i squared times log 2z, 2i, that is, sorry about that, divided by 2i plus 2i is just 4i. So some cancellation, some more cancellation, and you have e to the negative 2. So yeah, the result is looking pretty nice. You have pi divided by twice of e squared times log 2i. And this can be written as log 2 plus log I. And the imaginary unit is e to the I pi by 2 in the polar form. So once again, after the cancellation of the logarithm and the exponential term, you're left with I pi by 2. So our integral here evaluates to a complex number with non-zero real and imaginary parts. So we have pi times log 2 divided by 2e squared plus pi squared by 4 times e squared I. So that's a pretty nice result. So coming back to our equation, this implies that pi times, I'm just going to write it up here. This implies that all of this equals the integral over uppercase gamma plus the integral over lowercase gamma plus our target integral I. Now finally, we can turn our attention towards the integrals over the semicircular arcs. So for the arc uppercase gamma, any complex number on it can be written in the polar form as r times e to the I phi. That means the integral over gamma is that from 0 to, now phi here varies between 0 and pi, so we have the integral from 0 to pi of e to the I z, so that's e to the I r e to the I phi times log z again, so that's r times e to the I phi divided by r squared times e to the 2i phi plus 4, and the differential element transforms into I times r times e to the I phi d phi. Okay, cool. And we know that the integral over some contour gamma of a complex valued function f, we know that the modulus of this integral is less than or equal to the integral over the same contour gamma of the modulus of the exact same function f. So using the moduli and replacing the equality by this inequality, we have something like this. Okay, that does not look nice at all, but you get the idea. And because this modulus operator distributes over everything that's being multiplied or divided, we have the modulus of e to the I r e to the I phi, and I'm going to let me just simplify this out separately. E to the IR times e to the I phi can be written as e to the IR times the cosine of phi plus I times the sine of phi. So if you multiply out by I times r, you get e to the IR cosine phi. I squared means -1, so -r times sine phi. And using the laws of the exponential function, you can write this as the product of these two exponentials. So if you take the modulus of this, then you have the product of the moduli of these two exponentials. And if you have e to the I times some real number, which in this case is r times the cosine of phi, that evaluates to 1. And this is just a positive real number, so you don't need this anymore. You don't need the modulus or the absolute value operator anymore. So this sorts out to e to the -r times sine phi. And what about this log term? Well, giving separate attention to this one, to this term as well, we have log r times e to the I phi, and you can write this as the sum of the logarithms of r and the log of e to the I phi, which is again just I times phi. And what is its modulus? Well, that is just the square root of the square of the log of r plus phi squared. So we now have the square root of the square of the log of r plus phi squared, and we also needed the modulus of I r e to the I phi. So the modulus of I is just 1, and the same case for the modulus of e to the I phi again, and r is just a positive real number, so we're left with this r term, d phi divided by the modulus of r squared times e to the 2I phi plus 4. Okay, now all of this looks like a lot, and my cat has just woken up and he's looking at my screen right now with an expression that roughly translates to "what the fuck?" But no worries. The good news is that everything in the numerator is a positive real number. So that means we can make use of the fact that the reciprocal of the modulus of r squared times e to the 2I phi plus 4 is less than or equal to 1 by r squared minus 4. So again, replacing the equality by this inequality, we have r squared minus 4 downstairs. And what I'm going to do next is I'm going to factor out an r squared term from the denominator. So we have r squared 1 minus 4 by r squared, and one of these r terms cancels out quite nicely. Okay, cool. And what else can I do? Well, I can also factor out the square of the log of r term. And what happens if I do that? Well, all of this is going to become phi squared divided by the square of the log of r plus 1 times this log r term. And we're interested in the limiting case where r goes to infinity. Well, in that case, we have something bounded upstairs. And this term here is going to go to 0 as r goes to infinity. Same story for this term here. So in the denominator, you have r in the limiting case. And upstairs, you have the log of r. And log r by r in the limit as r goes to infinity is 0, meaning that polynomials grow much, much faster than logarithms. So everything here collapses to 0 in this limiting case. Okay, cool. So that's a relief. That means you can just cancel this out as 0. And now what about the integral over lowercase gamma? Well, because lower and uppercase gamma give exactly the same parameterizations for the complex numbers involved, the only difference being that we have to replace all the r's by epsilons, we have the same structure for the inequality. Notice here that I haven't canceled out an epsilon factor upstairs, and the reason will become clear shortly. However, again, I'm going to factor out this square of the natural log of epsilon term. So you have epsilon times log epsilon times the square root of 1 plus phi squared by log squared epsilon. And in the limit as epsilon goes to 0, this term here goes to 0. And using L'Hopital's rule, you'll find out that this term here also approaches 0, and e to the negative epsilon times sine phi approaches 1. Okay, cool. And the denominator just approaches -4. Okay, cool. So the entire thing collapses to 0 in the limit as epsilon goes to 0. So this is pretty cool. This is another relief. So we know now that the integral over the closed contour C equals our target integral I. And we also had something else with the target integral. Wait. Yeah, wait a second. Let me just backtrack a bit, and I think I erased that stuff. No, I did not. Here's the integral over the closed contour C. And yeah, I'm pretty sure I erased all that. Anyway, so it was this target integral plus I times pi plus the bonus integral, that from 0 to infinity, of the cosine of x divided by x squared plus 4. Okay, cool. So this implies that, what did this evaluate to again? Again, I'm going to have to backtrack all of this stuff. So I'm just going to copy this down. And finally, we conclude that by equating real and imaginary parts, that our target integral I equals pi times log 2 divided by twice of e squared. And this bonus integral of ours evaluates to pi by 4e squared, which is quite a nice result indeed. So yeah, that was awesome. I think this is my favorite contour integration so far. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.